Hello, I'm Dr Andrew Steele, and this is my Saga Spaces talk.
Hello there and welcome to this live Saga Spaces talk. I'm Gavin Ramjan and I'll be your presenter today. Saga Spaces has been especially created for you to experience live online talks with some of the most prominent minds and leading thinkers in the field of health and well-being. From sleeping better, improving your diet, exercise tips and simply being more mindful, we've got it all covered. Every one of our live talks is an opportunity for you to learn something enriching as we take you on a unique curiosity journey with lots of useful take-home advice to improve your well-being today. They're also fully interactive as well, so we'd love to hear from you and to take part as well from you guys as well in our live Q&A speaker session at the end. Now, today's talk is going to be fascinating. If you're anything like me, you'll have accepted without question that the aging process is inevitable. Well, prepare to have that notion turned on its head as we'll be exploring the cutting-edge scientific research that's paving the way to actually slow down the aging process and learn why the implications of these discoveries into aging have the potential to improve billions of lives. So let me introduce to you the man who will be enlightening us today. Our speaker is Dr Andrew Steele, an eminent scientist and biologist specializing in aging with a PhD in physics from the University of Oxford. He's also a popular science presenter and writer and the author of the book Ageless, the new science of getting older without getting old. Hello, Andrew, and welcome to Saga Spaces. Thank you for joining us.
Hello, how are you doing?
I'm very well indeed, thank you, cheers. Good to have you on. Before we get started, Andrew, I just want to ask you really effectively, what made you decide to become a biologist specialising in the science of ageing then?
Yeah, it's a good question. It's actually a bit of a funny story, really, because as you said in your introduction, I got as far as doing a PhD in physics. I was, well down the track to become a physicist before I realised that actually aging is our single most important scientific challenge. And I came to this realisation and changed my career effectively because of a graph. And I'm going to show you that graph during my talk. But I guess that sort of physics, very numerical, analytical way of looking at the world was the reason that I could change career because of a graph. And what happened was I moved from physics to computational biology, so that's sort of the data side of biology. And I found that as I was working in that field, I'd often know more about aging than the other very smart biologists that I was working with. And that's not because I'm some kind of genius. It's just because I'd read a few books, read a few papers on aging. Whereas you can get a great degree from a great university in biology and biochemistry and whatever it is, and not have a single lecture about aging, which is just remarkable. It's one of the most universal processes in biology, and yet it's widely, basically ignored by the larger biology community. So I decided that I'd have to, drum roll please, write a book about it, and this is my book, Ageless. And I wanted to try and sort of get some scientists and some doctors to understand that this is a really important subject to, perhaps devote your career to. But it's not just for nerds. It's also something that I think everybody needs to understand because, as I'll explain in my talk, I think this is the most important science of our time. So I'm really hoping to sort of spread the word and hopefully get some more funding for this science.
Yeah. Tell you what, cannot wait. I think it's going to be a really fascinating subject to learn more on. So I'd like to hand over to you then, Dr. Andrew Steele, for your Saga Spaces talk, Getting Older Without Getting Old, the Science of Slowing Down Aging.
Thank you very much and good afternoon, everybody. So as you just heard, I started out as a physicist, but decided to make this big change. And what I want to do in my talk this afternoon is change the way that you think about aging, just like, I changed the way I thought about it too. Because I think a lot of us think of aging as this natural process. We get wrinkles, we get grey hair, all our pets, our farm animals age as well. So it seems to be just this thing that happens to us, something that's, a part of nature, a part of biology. But I want to convince you, and this might sound slightly strange at first, that aging is actually our single largest humanitarian challenge. So I'm going to explain a bit about what I mean by that as we go through the talk. I think there's also this perception that aging is inevitable. It's just something that has to happen. It's not just a part of biology, but it's a process of falling apart that nothing can avoid. Not just biological things, but machines, they eventually get rusty and fall to pieces and so on. But what we found is that with brand new biology, we've got a huge new insight, understanding of the aging process. We have literally dozens of ways to slow it down and even reverse it in the lab. And what's really exciting is that some of these are already starting human trials. And it's this combination that's so exciting, because on the one hand, you've got what I'll hopefully convince you is our largest humanitarian challenge. And on the other, we've got the science that I hope can allow us to rise to that challenge. And I think the end result of this is going to be the biggest revolution in medicine since the discovery of antibiotics. It's going to completely change the way that we do medical care. But I did promise that I'd start by showing you the graph that changed my career. And so I'm going to show it to you now. It's actually quite a simple graph. It's just along the bottom, we've got how old you are in years, and up the side, we've got your chance of death in that year. Now, I think all of us know that older people are more likely to die, but just how much really shocked me. So let's stick the line on the graph there. I mean, just look at that. Let's go through that and try and put some numbers to this rather scary looking exponential graph. Let's start at the very beginning of life, on the very far left-hand end of that graph there. You can see that on your first year of life, when you're born, you have about a 0.5% chance of not making your first birthday. And, that's because you could be born with a childhood cancer or a genetic problem or something. But if you're fortunate enough to dodge those issues in that first year of life, actually life goes to being much, much safer for quite a long time. The safety continues to improve until you reach the age of 10. And current 10-year-olds have this rather incredible title. They are the safest humans in the history of our species. They've got a less than 1 in 10,000 chance of not making their 11th birthday. So if you've got any 10-year-old grandkids or nephews or nieces or anything like that, they've got this incredible title, and they're just such wonderful, happy, safe humans in the modern world. But unfortunately, as you can see from this graph, it's all downhill, or I guess uphill from there. So if you're 18, your risk of death is about 1 in 3,000. Making it personal for a second, I'm 38, so my risk of death this year is about 1 in 1,000. And let's just think about that for a moment. I quite like those odds, because if that were to continue for the rest of my life, I'd live into my 1,030s on average. But obviously, of course, that doesn't continue, and you can already see this is starting to increase. Actually, humans have something called a mortality rate doubling time. So what does that mean? Mortality rate is just how likely we are to die, and doubling time is how long it takes for that to double. And that time for humans is 8 years. So every 8 years, your risk of death multiplies by 2. And that means it can start out very small and actually stay quite small for quite a long time. But eventually, it gets very big very quickly. So if we get to the age of 65, there's about a 1% chance of dying that year. Now, that's still not so high. Like if you were to extend that out for the rest of your life, you'd still live into your 160s. But of course, unfortunately, 1% is now big enough that if you do start doubling that, you're starting to talk about some serious numbers. So by 80, you've got about a 5%, a 1 in 20 chance of death that year. And if I'm lucky enough to live into my 90s, or any of us in this audience are, but medical technology, aging biology hasn't advanced in the intervening time, the risk of death for a 90-something is about 1 in 6. So that's life and death at the roll of a dice. And that's just an incredible increase from 1 in 1,000 at my age to 1 in 6 at the age of 91 or 92. What on earth can be going on inside our biology to cause that to happen? So there are a couple of different ways to look at this graph, right? As a human, maybe it's a bit scary. You've got this exponential wall of mortality coming at all of us. But as a scientist, perhaps as a physicist coming to the end of his PhD, this is a fascinating idea. Because, what is it in our biology that's causing this incredibly synchronized increase in the risk of all kinds of different problems that means that we double in risk of death every 8 years? And this is just a fascinatingly universal phenomenon, right? So if I were to get one of you from the audience, or me, or someone from a country anywhere in the world, a person from an undiscovered tribe in the Amazon rainforest, I was to travel back in time to the 16th century and find myself a peasant farmer, our absolute risks of death would obviously be very different. But our mortality rate doubling time, this 8 years, that seems to be basically a universal fact about being human. So the real question is, what is this universal ticking clock? Why is mortality rate doubling so consistent within a species, within human beings or within other animals? What's going on? And I think the best way to answer this question is that we've got to ask another question, which is, what is aging? So aging, I think when we normally think about it, we imagine the cosmetic signs. That's the most common thing, to think about wrinkles and grey hair, the external changes that happen to our bodies. But these are very sort of superficial things, I guess. If we were to look inside our bodies, and what doctors might be more worried about with aging is the increased risk of diseases. And these, unfortunately, are the sort of depressing list of things that can happen to you as you get older. There's cancer, there's heart disease, there's stroke, there's dementia, there's diabetes, all these different problems. Now, you can obviously increase your risk of having these diseases. You can, eat a bad diet, you can smoke, you can not get enough exercise and so on. But ultimately, the single biggest risk factor, which is the sort of technical bit of jargon for what increases your risk, is simply how long ago you were born. And that means that there's something really important about this. You can be the cleanest living, healthiest 80-something, and you're unfortunately never going to have a risk of death as low as someone in their 30s, no matter what you do. And it's not just about death, of course. What aging biologists are really concerned about is quality of life. So other things that change as we age, we can become more frail. We can lose our memory, we can lose our hearing, our eyesight, and so on. And all these different kinds of loss, the way that I think of them really, is a loss of independence. They're a loss of the ability to do the things you like to get around and do. So, getting around the house, playing with your grandkids, going on holiday, whatever it is you enjoy gets harder as you lose all these various faculties. And there's also this sort of bigger picture loss of resilience. Our bodies get less able to repel external stresses. And this fundamentally is why it's so much riskier to get an infection when you're older. Because obviously infections aren't caused by the aging process. But at the same time, if you get the flu or if you get COVID, for example, and you're older, you're literally hundreds of times more likely to die than someone younger who got that disease. Of course, thankfully, we also have vaccinations, which can massively reduce that risk. And that's why it's so important to stay up to date with your flu and COVID jabs. A little public service announcement there. But what we can see is there's clearly something going on that makes our bodies just much less resilient to a whole variety of problems as we get older. And, when you think about it, going back to that graph, this does make sense. Why have we got this exponentially increasing risk of death? Well, it's because we've got a similarly exponentially increasing risk of diseases. If I were to show you the same graph for risk of cancer or risk of dementia, these things also go up in that sort of terrifying exponential way as life continues. And that's why we call them age-related diseases. Now, you might think that this is something that we in the rich world are sort of perversely lucky enough to have. Maybe it is that we live long enough to, we've managed to conquer a lot of these infectious diseases. We've massively reduced childhood mortality. We've doubled life expectancy in the last couple of centuries, which is an incredible achievement. But, it's only those of us in the rich world who are able to live long enough to experience these problems. And so what I'd like you to do now is just have a think. What do you think global life expectancy is? So this is the average length of time you'd expect someone to live in any given country in the world, not just the rich world. If we were to add up all the people on the planet, their risks of death, et cetera, what would be the average life expectancy in every country? And the reason I'm asking you to think about this is that I think the answer may surprise you. So the answer, and this is from 2019, because obviously some slight bumps in the road have happened in between times for the reasons that I think we'd all rather not talk about. But in 2019, global life expectancy was 72.6 years old. That's, I think, quite amazing. A lot of us imagine that there's a very poor developing world. They've got much lower sanitation, much worse medical care, obviously much lower income per capita than we have in the rich world. And so they live much shorter lives. But actually, although there obviously is still a huge disparity in terms of wealth, that disparity in terms of life expectancy is closing really rapidly. And don't feel bad if you got that wrong, by the way. If you ask people this as a multiple choice question, 3/4 of them or so get it wrong. And actually, if you ask university graduates, I think 80% of them get it wrong. So it's almost as their education makes us stupider in this way. We've got this idea that we live in some sort of incredibly privileged part of the world. And in many ways we do, but in terms of life expectancy, that sort of wealth is spread much more evenly than I think most of us imagine. And on the one hand, this is, I've already alluded to, I think probably the greatest achievement in the history of our species. More people than ever before have the possibility of living into old age, living a long, healthy life wherever in the world that they're born. But the flip side of this is that now most people in most countries are living long enough to get a fair old way up that exponential graph I showed you in our sort of first slide of the talk. And what this means is if you run all the numbers, about 150,000 people die every day on planet Earth from all different causes. And more than 100,000 of them, so over 2/3 of deaths, are caused essentially by aging. They're caused by the cancer, the dementia, the increase in risk of infectious disease, and so on. And this, fundamentally, is why I consider it our greatest humanitarian challenge. It's by far our largest cause of death. I would say, because those diseases, cancer can be very hard to live with, the treatment can be grueling. Heart disease, normally you don't just die of a heart attack, fall over dead, having had a perfectly healthy existence before that. It gradually saps your independence and, it can be a disease that lasts for years or even decades. And so I think it's our greatest cause of suffering too. So this could be a very depressing talk. But I think what I've hopefully shown to you is that this is a really big deal, right? And I'm going to try and turn things around now and give you a bit more of an array of optimism. So if we go back to looking at the slides, you can see this is that graph that I showed you earlier. So again, age along the bottom, risk of death up the side. And this, of course, as I said, is the graph for human beings, our risk of death doubling about every 8 years. So how's about we look at the graph instead for this little creature? This is a creature called the hydra. It's about 1 centimetre long. It's a pond creature. It lives in fresh water. And it first came to the attention of scientists because of its incredible regenerative powers. So if you cut a hydra in half, what you find is that you get 2 hydra. You cut the head, the head grows a new tail and the tail grows a new head and so on. And in fact, scientists have done this even more sort of macabre experiment where they put the hydra in a blender and you can cut it up into loads and loads and loads of pieces and you get loads and loads and loads of hydra. It's got this, regrowing a limb, that's nothing. The hydra can regrow its whole body from a single cell. So that's amazing enough. But also, while studying them, scientists have noticed something else amazing, and it's something amazing about their aging. So if we plot their risk of death with time, it looks a little bit more like this. Now, this is really quite astonishing, actually. It shows a risk of death that doesn't seem to change depending on how long ago they were born. It's about 0.2% per year. And we haven't done this experiment. We've actually watched them for about 10 years in the lab. But we think if we were to continue this experiment for 1,000 years, about 10% of the hydra would still be alive if this curve is accurate out to that time. And this is a phenomenon called negligible senescence. So negligible just means not much. Senescence is the biological word for getting older. And what this means is a risk of death that doesn't change depending on how old you are. Sometimes it's known as biological immortality. It's not real immortality. The hydra do still die, but they've got a risk of death that doesn't change depending on how old they are. So that's a really incredible thing. Aging doesn't seem to be a completely universal phenomenon. It's something that's common in nature, certainly, and all mammals that we know of, well, with perhaps one exception that I'll talk about in a second, seem to age, but there are animals out there that don't. Now, you might be thinking, Andrew, what can we learn from a centimetre-long pond creature? Its biology is completely different to ours. It's much, much simpler organism. We've got trillions of cells. Well, actually, it's not just pond creatures that have this incredible, negligibly senescent property. It's also this beautiful animal. This might make you think of One Foot in the Grave. It's actually one of my favourite animals for longevity reasons. It's called a Galapagos tortoise. And the oldest recorded Galapagos tortoise, we think, died when she was about 177 years old. Her name was Harriet, and she was brought back, we think, from the Galapagos Islands by Charles Darwin when he went on his famous expedition there. But the difference is that she survived Darwin by more than a century. And then she got to the age of 177 and she died of a heart attack. So she died in a similar way to a person, but pushed much further back in time. And these tortoises also have, what's more incredible than how long they live is that, again, they're negligibly senescent. They've got a risk of death that doesn't change with time. And what's, again, more impressive still than the hydra, because these are animals that are much closer to us in an evolutionary sense and in a sort of body plan sense, they're much bigger, we can see what they're doing. We can see that the tortoises don't become frail as they get older. Now, I realise tortoises aren't necessarily the best ambassadors for longevity. They're very wrinkly. It's not as if they move fast even when they are young. But a 150-year-old tortoise is just about as sprightly as a 50-year-old tortoise would be. And, just at some point during their life, they fall off a cliff. And that, I think, is something that we can really aspire to as human beings, staying as healthy as we can, as long as possible, and having the shortest possible period of ill health before, essentially falling off a cliff in a health sense very, very quickly. So that is something that's much closer to us. Another animal, I did say that I'd be talking about a mammal. You might be thinking, Andrew, that's a penis with teeth. It's actually an animal called a naked mole rat. And as you can imagine from the name, it's relatively closely related to rats and mice. But rats and mice, they live about 3 years in the lab, whereas a naked mole rat can live over 30 years, so more than 10 times longer than its other sort of similar rodent brethren. Again, it seems that all these negligibly senescent animals are sort of old and wrinkly looking and not necessarily something we'd aspire to cosmetically from an aging point of view. But again, because they're a mammal, they're like us, we can see that this negligible senescence doesn't just apply to risk of death. They don't become frail as they get older. They don't seem to suffer from any increased risk of disease. In fact, until recently, until scientists had big enough colonies of these in the lab, we thought that these guys were completely cancer-proof. We now know that there is the possibility of them very occasionally getting a tumour, but it's very, very rare in these animals. So, this beautiful creature, what is going on inside its biology? Can we learn anything from the naked mole rat? And, can we be a bit more naked mole rat? Perhaps, again, not in an aesthetic sense, but can we learn something from its biology that we can apply to human beings and try and do something about the aging process in us? Well, the answer is yes. And I already mentioned that scientists have made these incredible strides in the biology of aging in the last couple of decades particularly. And scientists have managed to identify a sort of set of underlying biological causes of aging. They're often called the hallmarks of aging. And in my book, I break it down into 10 of these hallmarks. And the idea is that these are the fundamental biological, cellular, molecular mechanisms that underlie all of those changes that happen as we age. Because when I answered the question, what is aging earlier, we talked about wrinkles and grey hair and cancer and heart disease and all these sort of endpoints of the aging process. And there are actually thousands of these endpoints. If you think about it, there are hundreds of kinds of cancer, there are dozens of different ways that your heart can go wrong, and so on and so on. But these hallmarks try and be simpler and more fundamental. They give us some insight into what's actually happening in our biology to cause these end stages of the aging process. And they range from a whole different sort of set of scales inside our body. So from the very smallest scale, if we zoom right in, my first hallmark of aging is damage and mutations to the DNA that's at the center of every one of our cells. DNA is this incredibly long molecule that stores essentially the instruction manual for how to build an organism, for how to make you. But as we go through our lives, we can accumulate essentially typos, mistakes in this instruction manual that can cause all kinds of age-related problems. Perhaps the most famous one is cancer. And so this sort of very, very tiny hallmark happening to the smallest molecules in our body can influence the aging process. We can then zoom out and cells themselves can age. I'll talk a bit about that in a second, so I'll leave that for now. Then we can zoom out a bit further and we can see that sometimes the aging of whole systems in the body is really important. So something like the immune system, one of the reasons that older people are more susceptible to coronavirus or flu or whatever it might be is because our immune systems weaken as we get older. And this doesn't just have an impact on infections, it also matters because the immune system is like our body's police force. So it often will clear out cells that look like they're at risk of becoming cancers, for example. And so as those anti-cancer defenses in the form of our immune systems weaken, that is one of the reasons that cancer increases with age. So I promised that I'd talk about these old cells. These are called senescent cells. Let's try and make this a little bit less abstract by talking about this really specific example for a minute. So senescent cells, senescent we've already come across from negligibly senescent, it's just the technical term for old. And these are essentially aged cells that accumulate in all of our bodies as we get older. And we've noticed that they seem to be related to a whole range of different age-related diseases. They're cells that have either divided too many times. So as we go through our lives, cells divide and divide to replace cells that are lost. And if that happens a lot of times, the cell can become senescent. They can be cells that have accumulated too much of that damage to their DNA. And so the body thinks they're at risk of becoming cancerous. And so what the body does is it slams on the brakes. It says, this cell, you can't divide anymore. You're just going to have to sit there essentially doing nothing. And firstly, that's not great because it means that it's not doing the job that it's meant to be doing. It's not dividing and replenishing your tissues. But secondly, there's a bigger problem here. And that's that these senescent cells emit a toxic cocktail of molecules that essentially accelerates the aging process. Now, again, this might be quite depressing, apart from the fact that scientists have developed drugs called senolytic drugs that can clear out these aged senescent cells while leaving the rest of the cells of the body intact. And they've done this in mice. So they waited till the mice were about 24 months old, so 2 years. And obviously mice, as we've already mentioned, live a lot shorter than humans do. So that's roughly equivalent to sort of 60 years old in human terms. So these, maybe late middle-aged mice got given the senolytics. It clears out those senescent cells. And the mice essentially got biologically younger. And that's a really incredible result. So the first thing is they lived a bit longer, which I guess is a good thing. But they didn't drag out that period of frailty at the end of life. They were healthier too. They got fewer diseases, so less cancer, less heart disease, fewer cataracts. They can run further and faster on the tiny mouse-sized treadmills they use in these experiments. They basically send the mice to the gym and see, if they're becoming frail at a slower or more rapid rate. They become more curious. So it seems to reverse some of the cognitive aging. And frankly, it's really worth just doing a web search for some pictures of these animals that have had the senolytic drugs because they just look great. You do not have to be an expert mouse biologist. I was a computational person when I was working in biology. I never worked with mice in the lab, but it's just so clear which of these animals are the same age, but the one that's had the drugs, they've just got thicker fur, less grey fur, plumper skin. They just look like they're younger animals. So this is hugely, hugely exciting. Senescent cells are a hallmark of aging. They seem to be responsible for most, perhaps even all aspects of the aging process are somehow connected to cellular senescence. And by clearing out these cells, we can have this really widespread impact. Now, you might be thinking, again, this is something that's maybe it's 50 years away. It's a sort of development. They've got it working in mice in the lab, sure, but when are we going to see this in humans? Well, actually, there are already 20 or 30 companies that are trying to turn this from something that works in mice to something that works in people. And human trials of these drugs have already begun. So this really isn't sort of pie in the sky theoretical biology. This is something that could happen really, really soon. And, we could certainly get the results of these first trials in the next 5 years. Just thought I'd mention another couple of things that could also happen in the very, very near term. these are the ideas of repurposing existing drugs. So these are drugs that we already use for something else, but have shown some evidence that they can slow down the aging process. And one example of that is metformin. Now, a few of your ears might have pricked up in the audience when I mentioned that, because some of you are probably taking metformin or know someone who is, because metformin is the most common anti-diabetes drug. It helps to maintain blood sugar levels if you've got type 2 diabetes, the sort that's associated with aging. But what we've noticed is that people who take metformin seem to do better in other ways, and there's some evidence that it might slow down the aging process. And so the idea is that scientists want to do a proper randomized trial where they give this metformin to a bunch of people and see if it really does slow down aging. And if that works, this is a drug we've been prescribing in the UK for more than 50 years. We really understand a lot about its side effects, which are fairly minimal. And so we could start rolling it out for literally pennies per pill. It's an incredibly cheap, incredibly near-term potential intervention if we can just get that trial underway. Another example is a drug called rapamycin. And this is the single most effective drug in the lab at slowing down aging in mice. And what's really cool about this is actually due to an experimental accident. The very first mouse test of rapamycin that was really rigorous was done in 2009. And because of essentially an experimental mistake, the scientists weren't able to give the rapamycin until the mice were already 20 months old, so quite late in their lifespan. And the scientists actually were expecting it not to work. They thought, we've screwed up here. We can't give the drug until very late. So if it slows down aging, if we slow down aging late, we might make a little difference to lifespan, but will we really see? Well, actually, even when given at that relatively late stage, it extended the mice lifespan by about 10%, which is a really incredible result. And it's so robust in mice. And there are some human studies that show it might be able to improve immunity in older people, actual, human people, not mice people. So this is a really exciting idea. And again, we just need a proper human trial to work out whether this pre-existing drug, that again is off patent, which means it's able to be produced very, very cheaply, could be repurposed as an anti-aging medicine. I thought I'd just finish off with a couple of different things. First of all was to quickly mention some of the ethical questions that I always get in these talks. Because, I think one of the first things that often springs to mind is, could we cure aging? Could we potentially address this huge humanitarian problem? But would we create problems that were larger than the ones that we were solving from a sort of health point of view? And the most common question I get is, what about population? If we were to suddenly slow down the rate at which people were dying, increase lifespans, would that cause all kinds of impacts on the planet? We already know that climate change is increasing global temperatures. We're emitting all kinds of other pollution other than carbon dioxide, microplastics. It's in the news every day. So would having more people make this worse? Well, I could give a detailed answer, but what I want to do actually is give you a sort of a more of an overview answer, which is something that you can apply to a lot of these different age-related ethical questions or aging-related ethical questions. And the first thing is something called the reversal test, which is to imagine the question was turned around. So you imagine yourself to be in a world where aging doesn't exist. People are living much longer, much healthier lives. There's much less cancer, there's much less dementia, and so on. But there's whatever ethical problem you're worried about. So let's take the example of population. We've got billions and billions of people on the earth. Huge environmental strain is being caused by all of these people. The question is, given that there's no aging in this hypothetical world, would you invent aging to try and reverse that damage that we were doing on the environment? I really don't think you would, because, first of all, you try and cut back your carbon emissions in a more conventional way. You'd change your diets, you'd change the ways you got around, you'd look at ways to generate electricity that were lower carbon, et cetera, across all different kinds of pollution. And if none of that worked, if you decided that the only way you could do this was killing people, then I really suggest that should be a method of last resort. Would you do it by inventing this decades-long process of disease and decline and decrepitude? Again, I just really don't think you would. And the other ethical question to ask yourself is, how is aging research actually different to other kinds of medical research? If I had just given a talk on cancer, I wouldn't get a single question about population or about immortal billionaires or whatever it was at the end, because other scientists who are working on specific diseases are just trying to keep people healthier for longer too. And so I've never come across a reason why this kind of research is any different from any other kind of medical research. So those are really general answers. And if there are any more specific questions, I'm sure we can get into those in the Q&A afterwards. I also thought I'd finish with a little bit of health advice, because this is a really fascinating, exciting time to be alive, right? I genuinely believe that the first generation of these anti-aging drugs could be with us in time for most people alive today, even people who are already a little bit older. And that means there's this hugely exciting opportunity. By trying to keep yourself healthier for longer now, you can potentially live in a healthy state long enough to enjoy some of these new treatments. So the first thing I'm going to do is tell you the sort of basic health advice you've heard it's all true. If you don't enjoy exercise, I'm afraid that is the single most important thing you can do. Eating a healthy diet is really important. If you smoke and want to live a long time, the first thing you need to do is quit smoking. This can sound quite boring. It can sound like advice you've heard hundreds of times before. But once you understand something about the aging biology, you realize that these things literally slow down the aging process, which I think makes them a lot more exciting. And, I'm certainly much more motivated to go out for a run when I'm a bit tired in the morning, if I know that I'm literally slowing down my aging, not just improving my muscle strength and cardiovascular health and so on. These things have a much wider benefit. Exercise can even stave off dementia and certain kinds of cancer. So it's got this huge effect on your biology. The second thing it can do is show you how slightly less conventional bits of health advice can improve your life expectancy and your health span. So actually brushing your teeth, there are obviously very good reasons to brush your teeth because you want to avoid the tooth pain and expensive trips to the dentist. But actually we now know, because we understand a bit more about the aging process, that keeping good oral hygiene, so getting rid of gum disease, getting rid of tooth decay, can reduce something called chronic inflammation in our bodies that seems to reduce the risk of heart disease, can even perhaps reduce the risk of dementia. So that's just another really great reason to get on top of brushing your teeth and flossing and all that stuff. And finally, I think the best thing you can do for everyone's life expectancy, actually, if you're already following a lot of the basic health advice, is to spread the word about this aging biology stuff. Because, if you want to live a long time, if you want your friends, your family, your kids, your grandkids to live a long time, everyone around the world, people you don't know, the single biggest thing that can move the needle is research into aging biology. It's understanding the process of aging and what we can do about it. Because you simply can't, unfortunately, exercise your way to guaranteeing yourself to live to 100. It's just, the odds of making it there are just too small. But if we understand something about aging and we can keep people healthier for longer, I think that's the single most important thing that we can do. Because this is medicine that's going to transform the way that we do medicine. I said it would be the biggest revolution since antibiotics. The reason I think that is because these are drugs that are going to potentially prevent multiple different diseases. Just as penicillin can be used against a variety of bacterial infections, so too can an anti-aging drug, a senolytic drug, for example, be used to prevent not just cancer, not just heart disease, not just dementia, not just frailty, not just memory loss, but perhaps all of these things, perhaps even the wrinkles and grey hair at the same time. And this is a really, really exciting idea. And I also think it's just so important that older people can advocate for this. It's all very well for, me sitting here as a 38-year-old saying we've really got to invest in this anti-aging stuff. But, it's people who are my parents' age who are really, at the sort of sharp end of aging, who are starting to experience it themselves. I think it would just be so, so powerful if older people could be advocating for doing something about this as well. So if you want to learn more, I may have mentioned that I have a book that goes into obviously a lot more depth than I managed to over the last half hour. Again, the idea is it's accessible to everybody, not just scientists. It breaks down why we age. There's a little bit more health advice in there. And there's also some real detail in the science on how it is that scientists are trying to intervene in the aging process. And I think that's probably about all I've got to say for now. So thank you very much.
Andrew, thank you so much for your fascinating talk today. Absolutely loved it. And thank you to our audience members as well for watching. I hope you'll join us again next time for another Saga Spaces talk. We'll see you soon.